who am I? I work for a company called CityStorageSystems, small startup. Nobody probably knows about us. We're still in a stealth mode. We're also known as cloud kitchens. What we're trying to do, we're trying to make on-demand food affordable. You know, when you order food online and want to get it delivered, it's actually really expensive. There's like term $10 burger problem. You want to pay $10 and you pay 20. It's kind of not really great. And myself, I have a background in data systems. I built something like a database before. I was like very early at CSS, worked on data infrastructure, and right now I'm responsible for entire software infra. And what we're going to be talking about, a little bit about operational data, analytical data, maybe we're going to talk about cloud migration, and an underlying infra. We're on a really tight time budget, so we'll see how far we can get. Let's go. Why streaming? So if you think about kitchens, or like we call them facilities, it's a many micro factories stuffed in the same building. And they, you know, activity happens in real time. Why is it, you would ask? Well, because if you're a person who wants to eat, you will send an order. You will send an order to a platform like Uber Eats or DoorDash or wherever. It gets to a person who will need to cook. What is cooking? Cooking is a process for taking raw material, applying some tools, and converting it in a final product, which then needs to be, guess what, carried out and delivered to you. And if this looks like a bunch of containers, that's actually on purpose because that's what it actually is. Kitchen is almost like a unit of scalability for a brand. Like think of, I don't know, McDonald's, right? They have some throughput characteristics, how many food items they can cook per hour, per minute, you know, probably per second. And when you stuff multiple kitchens under the same roof, which creates almost like a factory of microfactories, then you also have the situation with logistics inside that setup, right? That's why you have this robot, which is kind of carrying stuff from kitchens to a delivery driver, which actually later tries to batch, right? So some ideas just placing in your head about how you can reduce cost of delivery in this setup. Right, so the order, the food order goes through multiple states, right? It's placed, then you need to negotiate delivery, then you need to cook, and then before cooking you need to print a ticket, right? It's like a state machine if you think about it. The truth is it's a very complicated state machine because things happen in parallel. Right, the order negotiation can be happening together with cooking. Some things need to be ordered, some things can be parallel. It's very complicated. So the way we thought about it that, okay, each order will run will be represented by multiple different state machines. And how would you implement it? There's multiple ways. We decided to go with something that reminds me if somebody was doing, you know, software development 20 years ago, there was a concept called enterprise service bus. It's kind of similar. There's like something that imports orders. Then there is this bus. We used Kafka originally. And then all the information, all the events are going through this bus. There's multiple subscribers that latch on those streams. They take event, they look at it, and they react if needed, right? That's how sequencing is done. For example, if new event come, new order came, some processor took it and it sees that event needs to be, like order needs to be printed, it would execute printing and will record it back on the bus. And then so on and so forth. The problem was that, you know, stuff is sequenced. Kafka has partitions. You can grow them to a fairly large number. However, you still can go really crazy with them. And head-of-line blocking is a very big problem in this world, right? It's not data processing world where you take batches and, you know, if they're late for an hour, who cares? It's real time. Now, what would you do? It would be really good if you can do something like that, right? If you can have a queue per order, think about that. And have it dynamic and have it multi-regional because we everywhere, right? We multi-regional. So we looked at a couple solutions back then. That happened a couple of years ago, and we also run a database. We still run it. It's called CockroachDB. So we took all this information and we built something in-house. We call it K'd event queue. So it's a planet scale, means it can scale to multiple regions, continents, doesn't matter. And then the way it works, it lets you create topics, and topics will be partitioned by IDs of messages of like queues which you inject. And that whole thing is dynamic, right? New order is registered, we write it in, new partition automatically created. That actually simplified a lot of in terms of development and thinking about scalability. And if I have time, when I'm going to talk about cloud migration, I'm not going to be talking about this specific system because it was trivial. When we needed to move to another cloud, we just took this database, we expanded it, we moved all the data, contracted, done. Consumers and producers were moved automatically. All right, so if you're interested, we can talk about it. We're thinking about open sourcing if there is an interest in the community. Next, big data, doing its streaming. The fundamental question I feel many startups ask, many founders ask. There are startups in streaming data world, like we today on this stage talking about it. And the question, in my opinion, is yes. I call it truth to know gap. The world is dynamic. Stuff happens all the time. The time it takes for you to learn about the world, however, is a time gap. There's many factors. It could be data is too slow. You get in data every month, so you'll have a 1 month gap. It could be that your data is broken, so it could be infinity. You will never actually learn. Now, broken data is a separate question, but data velocity is a thing that we can actually try and address. And then that's why fundamentally I believe that every data infrastructure those days should be based on streaming. My personal opinion, and I was lucky that CEO of this company was also into real-time data and knowing things really, really, really fast. Because every CEO has those questions, all right? They want to know what's happening. Like, if you ask them, do you really need accounting data once a month? They would only once a month. They probably, yes, yeah, fine. But if you tell them, what about, like, do you know? Do you want to know every day, every second? Nobody will say no. And when you go down with questions, they get more interesting, right? The final question about competitors. Again, business is a harsh world. Whoever gets data first makes decisions faster. If data is correct, they will make probably, hopefully, correct decisions. Well, they have higher probability of making right calls. So I do think that real-time data is a fundamental right of any CEO, right? They need it, and we have to deliver as a tech community. So with that in mind, how can we do it? There's a bunch of buzzwords, data mesh stack. I just Googled stuff, and it's actually very annoying. I recently found myself not being able to tell what group I was managing before, big data, data lakehouse, and we just need a database. All we need, a normal database. I can write, however, this database doesn't exist. And that's why I started calling our stack data intelligence infrastructure, just to cover all the buzzwords, one buzzword to cover all of them. And here's design. That's like a revisit. You can see that Kafka was replaced by KQ. Again, it's multi-regional or planet scale, multi-cloud, multi-wherever, Q. And there is this exporter which latches on real-time events and moves it into Kafka, right? Because Kafka is cheaper, right? That's the main reason. We take it to Kafka, and one of the first big decisions we needed to make is a data format back then, or table format. We looked at Iceberg, we looked at Delta. Delta was really young. We picked Apache Hudi because it allowed us to support incremental order of our processing. And Trina was our database query engine of choice. Later, we introduced Flink for stream-on-stream processing. And then that's actually sequential time-wise. There is no batch because we didn't have any batch. And only later, we realized, well, actually, batch is coming. I'm sorry, guys. That's the part about not remembering the next slide. We realized that it's all good. We write in data incrementally in very short batches because we can go down to minutes. But it still wasn't enough for some use cases, and we brought Apache Pinot, real-time lab database. We picked it mostly because of the promise that upserts would work, and it's been fine. We added ClickHouse recently to our stack for some use cases, but Pinot still, still working and still absolutely okay. So if you worked with Pinot, you know that it's a built on Lambda architecture, so you need to push data periodically to make sure the state of the world actually exactly the same as in Pinot, because it's best effort consistency, and we used Apache Flink for that. So this one is not open source. Well, I think it was implemented. I might be wrong, actually, but we were the first who did it. And finally, batch transformations came a year later. We used Trino. We developed our own incremental writer. We call it Data Ingestion Manager. It's also responsible for transformations. We also replaced Flink to Pinot connector with Trino to Pinot connector, which we open sourced. We support writes, right? That's PR is still in review on Trino side. And as a final stroke, we also made Trino be able to read from Kafka. Right. If you think about it, as I said before, we just need a database, a simple single database, and we thought Trino is fairly good for actually querying this data. There were actually funny ideas. What if we can schedule real-time pipelines using Trino? Why can't I do create real-time table? Because we implemented create Pinot table, which could actually consume from a real-time stream. But we haven't implemented it, so they're still just ideas. All right, next one, time check. Okay, I have time. We can talk about cloud move. So we had all this infra, and we needed to move clouds. Why? Well, cost, guys. It's actually really useful when you can move from one place to another. And then honestly, in a lot of systems, data is the one that is taken hostage, right? It's really expensive to move it. So a couple learnings. How did we do it? The first, that's a setup. I didn't connect Trino to all these data sources. Just imagine it talks to everything and pulls from everything. And all the consumers of data stack, analytics and stuff sit in Cloud One. The first thing, we replicated Kafka sources. We started from the root, right? Source of truth, all the input streams. Now, if you didn't know, here's a cool thing. Getting data outside of clouds is very expensive. There are companies which can make it actually up to 4 times cheaper. We can talk about it offline if you want to know exact names. Another one, well, I'm not advertising, so that's what I'm saying. So a next step was we realized that we need to move blob data. Moving blob from cloud to cloud is extremely painful. Now, for once, right, all things like it could be you're running on Google, so you use JS as a prefix. You go into Azure, they use something else. So we implemented this layer. We called it right now Cloud as a Blob. It wasn't called like that before, but it's transparent, almost like a proxy. That's how it started, which let us completely abstract cloud blob. Later, what we found, because now everything goes through this layer, we could implement very interesting optimizations like caching. Like we can actually store small files. And the most interesting, if you pay attention to pricing of those cloud vendors, you would learn that some operations are more expensive than others. For example, list is extremely more expensive than get. Why is that? That's why, by the way, we started doing in big data community all this metadata. Let's pack all the metadata in a single file. Well, guess what you can also do? If you have this layer, you can do list from this layer. And the reason we have to build all of it, because the destination cloud, their blob solution wasn't as scalable as we actually used to. So we had to shard. We decided to shard on an infrastructure layer. All right, next layer, moving Pinot was pretty easy. Through this layer, move Pinot data from, like we were moving from Google into our magical layer, and then flip bring up compute and replicate. What was most interesting is that we replicated other pieces of data. We didn't do stop the world. We have to do it while engine is running. So for every single data set, we replicated a bootstrap data set. And of course, while it was replicating, the data was actually moving forward. And then we recomputed all the deltas. Because we were ingesting data, the main replication for real-time data was root, Kafka, right? Our idea was that if we replicate the root of the tree, of the data tree, of this DAG that spans all the data sets, and then we one by one replicate like those specific tables, right, in this case, they will actually eventually catch up, and then they will get to the same actual level. Now, it's not actually true, because if somebody in their code used any undeterministic functions, like current time or wherever, it will never converge. And it didn't in our case, but we did some spot checks, and we actually compared every single data set to see how divergent they are. Now, to never have this problem again, in this cloudless blob layer, we implemented incremental replication to other regions. So if we were to move again, we won't have the same situation. All right, let's go next. And then once we validated, we did a flip. It was easy. Let's talk about money. I do think that's a big annotation. A lot of engineers complain that when they interview, we ask them to do this, what is big annotation of the stuff? And when they join, nobody cares about actual money. Well, that's actual big annotation. How expensive is your system? Because if it's too expensive, company goes bankrupt. Or your open source project never takes off because it can't compete. And then it's surprisingly how many companies don't care. Or say, well, it's bottom line, wherever, our revenue is infinite, infrastructure can save so much. We have a different approach. We run Kubernetes for every single system. Because we picked Kubernetes, it let us do some interesting stuff. It made it extremely painful in the beginning for core infra team, which is responsible for Kubernetes, and for other infrastructure teams. Because Kubernetes is not as simple as it is. It's programmable. Which means if you want to use all the features, you have to learn it and go really, really deep. However, if you do it, you can do something like that. So the way we approach it, for open source systems which we're playing with, we use Helm. We usually use open source Helm. At least we try. 95% of time it doesn't work because of some customizations we did inside our clusters. And once we modify and make sure it runs and we're happy, we actually write our own custom operators. We have an operator for Cockroach. For Kafka, we use Streamzy. It didn't go really well because of opinions around this operator. Flink, we still use open source. And Blob custom, so it's Pinot custom. So it's just we're slowly rewriting everything into our own systems because we do believe machines should be handling on-call, and then scaling, and then dealing with issues, dealing with provisioning, dealing with we had a lot of networking issues. That all should be handled automatically. So it helps us to maintain very small team sizes of actual engineers. We don't have ops who, if we encounter the problem, just modify one of the operators, right, and we'll never talk about problem again. And we implemented some internal additional auxiliary things which we run in our clusters. Diagonal autoscaler. We can, there's a couple startups right now which lets you scale pods vertically and horizontally. And we did it because we wanted to scale them down, right? Engineers sometimes ask for 10 CPUs. They only need half of CPU, right? That's one of the really big wins. Disk autoscaler, it's pretty tricky in Kubernetes, actually, unless you run on clouds that supports it. We don't have it, so we built it. Node auto-healers. Kubernetes is not bulletproof. Sometimes stuff starts and it's broken. Sometimes stuff runs and then it breaks. We saw, I talked about Blob. We see sometimes instances of VMs not being able to talk to Blob. What would you do about it, right? Or freezing. So there's almost this doctor constantly running and fixing things. And many other things, for example, Trino, I mentioned, we run at our own version. The system runs usually around 70 to 80% CPU utilization, just like FII. It handles ad hoc and ETL and batch all the workloads. How did we achieve it? Again, auto-scaling and custom operator and all custom, but means, writing code. So I think that's it, folks. And I'm right on time, actually. Wow. If you're interested, we've started our blog post, our tech blog, recently. So there's like, number of articles is growing, but because we try to be smart with names. If you want to learn about some systems I talked about, KUQ, it's reliable order processing. Sharding, it's a system that helps KUQ to shard and move data around, between nodes. That's the latest blog post. There's something about robots, which also use those systems. Something about machine learning, because figuring out when food needs to be cooked is a tricky question. Again, it's like a factory. But you assemble things which are not really common sometimes. And quite a bit of articles on Kubernetes, because that's our foundation. And that's it. Thank you, guys.